So hello and welcome to this first lecture on gravity in non-relativistic quantum mechanics. So you can find all the information about the lecture on the Moodle page. In those videos I want to just present the material for the course, and we will have weekly meetings via Zoom. And yeah, all the information about exams, additional material, the script for the lecture, you will find all of this on the Moodle page for this course. Before we start with the actual topic for today's lecture, I want to give a brief motivation of what we're doing in this lecture. Why consider gravity in non-relativistic quantum mechanics? What is interesting about this at all? So the usual picture you probably know very well. The way it is presented is that we have quantum theory, both in the form of non-relativistic quantum mechanics and relativistic quantum field theory. And on the other hand, we have general relativity that describes gravity, and both of them have turned out to be very accurate theories that in their specific realm of applicability give us really precise predictions. And then the problem is often presented as one where it becomes important under very extreme conditions, like in the early universe or in black holes, where you have both strong gravitational fields and high energies and small length scales, where the theories we have break down and there is a need for some quantum theory of gravity. And so the underlying idea behind this is usually that the equations that govern gravity are Einstein's field equations. So if you want to write those down, you have r mu nu minus 1/2 r g mu nu equals 8 pi g divided by c to the 4th t mu nu. So those are Einstein's equations, and the right-hand side of these equations describes matter. Matter curves space-time, so the left-hand side is what actually belongs to space-time. The curvature tensor R and Ricci scalar describe this curvature of space-time. G mu nu is the metric, and in principle all those quantities of this left-hand side, also sometimes called the Einstein tensor, all these quantities on the left-hand side can be derived from G mu nu, from the metric. And the metric is also something that lives on space-time. So with every space-time point there is a metric. So this is actually a field on space-time, and behind this there is the idea to just apply the methods known from quantum field theory. Say, well, we have this field G mu nu, so let's just apply what we know that works for the electromagnetic field, for example. Let's just quantize this G mu nu. And this fails because the quantum field theory you get turns out to be non-renormalizable. So as a quantum field theory, general relativity somehow does not work. And this is the usual story. And based on that, then people often say that, well, things go wrong at high energies when this renormalizability starts to become a problem. But at small energies, everything is fine. We can just use this field theory, even though we know that it's non-renormalizable and that it breaks down at high energies. We can still use it to make predictions at low energies. So yeah, so this relation is, however, not the full truth. So a very nice picture on how the different fundamental theories that we have and that we use in physics are related to each other, even though you have to take it with some grain of salt. But as a nice illustration, you can look at what is sometimes referred as the cube of fundamental theories. So for this, you draw three axes on which you put the three fundamental constants that we currently use in nature. First, you can put the gravitational constant, g. On the second, you put h bar, or h, quantum for quantum mechanics. And on the final axis, you can put the inverse of the speed of light, 1 divided by c. And now you can think of basically starting from standard classical non-relativistic mechanics. So non-relativistic classical mechanics. You can start from there, and we know, well, historically the first was when we introduced the finiteness of the speed of light, then we end up in a corner here, and here, we end up with special relativity. On the other hand, we can of course introduce the gravitational constant, and we end up with Newtonian gravity here. Or you introduce h bar and you end up with quantum mechanics, non-relativistic quantum mechanics. And now there are different attempts to unite those theories, to combine those theories and go to areas where two of those constants play a role. So you can go to this realm where you basically unite the principles of special relativity with gravity, and of course we know that this brings us to general relativity theory. And on the other hand, we also know that if you try to find a relativistic version of quantum mechanics, a special relativistic version of quantum mechanics, we then end up with relativistic quantum field theories. And now, of course, you see that there are essentially two roads that lead to what we want to have, which is some theory of quantum gravity, right? Some theory where all three of those constants play a role, where we have gravity, where we have quantum, and where we have relativity together. And those are the typical roads that are taken. You can either start from the principles of quantum field theory and try to somehow include gravity in the picture, or you start from general relativity and somehow try to quantize this in order to get to a quantum picture of gravity. So those are the two typical roads that are thought to bring us to a quantum theory of gravity. But now if you look at this, then you see that essentially those points form some sort of cube, but this cube is incomplete. We have here also the backside of this cube. We have one more corner of this cube that we did not discuss yet. And this is this corner where you have essentially Newtonian gravity and non-relativistic quantum mechanics. So you could call this, if you want, you can call this non-relativistic quantum gravity. And this is exactly what we are interested in and what we want to look at in this lecture. That is the question, well, if we try to understand this corner first, the corner where we have gravity and we have quantum mechanics, but we leave relativity out of the picture for now, can this teach us something about what the full theory of quantum gravity looks like? Is there maybe some road along this edge to get to the theory of quantum gravity? So this is in a simple picture the idea of what we are trying to do. So now, of course, I've just told you that you can basically just quantize Einstein's equation and get some perturbative quantum field theory for general relativity, also sometimes called perturbative quantum gravity. And of course, if you believe that this theory is correct, then there is nothing wrong with it at low energies. So, so you would, in principle, think that the results that are relevant in this regime can be derived from this theory. But it is important to notice that, well, first of all, some results are just difficult to calculate from such a full quantum field theory for gravity. We don't usually use quantum field theory to derive results about quantum experiments in the lab. For example, if you do quantum optics experiments, you don't usually use full quantum field theory, but you use quantum mechanical methods. So in the same sense, one would also ask, okay, can we use the formalism of quantum mechanics and just introduce gravity into that, and what are the things we have to consider there, what are the difficulties that can emerge when the principles of general relativity enter in non-relativistic quantum mechanics. And the other question is, well, is it correct to use this quantum field theoretical description of gravity in the first place? Because you have to keep in mind that whereas this theory only breaks down at high energies, it is not experimentally tested at any energy. So there is no experimental evidence that it is true even at low energies. We just know that at low energies it works as a theory, and at high energies it does not. But the fact that it works as a theory at low energies doesn't mean that it's the correct theory. And especially the fact that it does not work at high energies should make you a little bit skeptical whether or not this is the right theory at low energy. So the question there is, well, could there be some alternative truth? Could there be some other theory that is correct at low energies? And is this treatment in analogy to quantum field theory of gravity maybe not correct in the first place? And that's also what goes wrong at high energies then. So this is in short what this lecture will be about. So, and this also points out the two different focuses we will mainly have. We will, on the one hand, we will ask ourselves, okay, how can we describe quantum systems, non-relativistic quantum systems, in the context of gravity? So what happens if we have some laboratory quantum object, like particle, in a gravitational field? And on the other hand, we want to ask, okay, how do we treat quantum gravity, or do we need to quantize gravity at all? And are there any effects that one can observe in quantum mechanical experiments that depend on whether or not we do have such a quantum theory of gravity? And we will come to those points. So with this, we can come to the topic of this first lecture, which is the Einstein-Podolsky-Rosen, or also short EPR argument. You might have heard of this already in your quantum mechanics lectures. To warn you right in advance, it has nothing to do with gravity, but the question is, if we want to understand gravity in the context of non-relativistic quantum mechanics, as a first step, we should try to understand quantum mechanics itself, and we should try to understand what possibilities do we have to make changes to quantum mechanics, and which possibilities do we not have. A very fundamental step in our understanding of quantum mechanics and what it actually means, in which respects the quantum world is different from the classical world, was the argument by Einstein-Podolsky-Rosen. And it was published in a paper in 1935. So yeah, this is the paper. Can quantum mechanical description of physical reality be considered complete? And the title already tells you which question they were after. They were asking whether quantum mechanics provides a complete description of the world, or whether something is missing in the theory of quantum mechanics. As you can already assume, their argument was that there is in fact something missing from the theory of quantum mechanics. And before we come to the paper, which we will discuss in a slightly different version that was presented a bit later by Bo, that uses spin rather than position and momentum, as Einstein-Podolsky and Rosen did. So in order to do this, we will first briefly review what you probably already know about spin and the measurement of spin in quantum mechanics. So let me start with recalling briefly how we present the state of a spin 1/2 particle. So we can, first of all, if we have a particle with a spin, we can represent it in terms of the eigenstates of the spin in z direction, which is given by the Pauli matrix sigma z. So if we have this Pauli matrix, we have the two eigenstates, which we call spin up and spin down. The spin up state is the eigenstate with eigenvalue +1, and there is the state down, which is the eigenstate with eigenvalue -1. So the Pauli matrices are given in the usual form in this basis. So sigma x is 0, 1, 1, 0. The Pauli matrix in y direction is 0, minus I, 0. And finally, the Pauli matrix in z direction is diagonal as 1, 0, 0, -1. So with those, you can form a vector that has those 3 as its components. So we basically form the vector sigma which is this. And you can then consider the spin in an arbitrary direction. If you have some unit vector A, you can just consider the scalar product sigma dot A, which is again a matrix of this form, so a 2x2 matrix. So yes, so sigma dot A is again a 2x2 matrix, and it also has two eigenvectors with eigenvalues plus and minus 1, which we can call chi plus minus, which you could write as a normalization factor. And then if A, X, Y, Z are the components of this vector A, of this unit vector A, then this would be AZ plus or minus 1. And the second component is AX plus IAY. So those are the eigenstates for the spin in general direction. And we have the Born rule that gives us the probability of finding either of those eigenstates after a measurement with their corresponding eigenvalues. So the probability of measuring the eigenstate, the eigenvector, the eigenvalue plus 1 is the projection of the state chi plus onto the state psi that our system is in, absolute value squared of this. And the same way we have the probability of measuring the eigenvalue minus 1, which is chi minus projected on psi, absolute value squared. And after the measurement, so this is the one part of the Born rule of the axioms of quantum mechanics, and the other part is that after the measurement we will find the system in state chi plus here, and in this case we will find it in state chi minus afterwards. So this is the collapse postulate of quantum mechanics. If we make a measurement of the spin, we will find the two possible outcomes, plus 1 and minus 1, with these respective probabilities, and after the measurement the state will jump from psi to whatever eigenvector belongs to the state. So for the discussion that follows, we need to consider 4 specific eigenstates. We consider the 2 that we already had, the states up and down, which are sigma z eigenstates. And in addition, we can define the eigenstates, the states plus, which is just 1 divided by square root of 2 up plus down. And we can just define the state minus, which is 1 divided by square root of 2 up minus down. And those combinations are actually the eigenstates of the polymatrix sigma x. So those have the property that sigma x acting on plus is plus, and sigma x acting on minus gives minus the state minus. So if we would represent those as vectors in the basis up down, we could write them as 1 over square root 2 1 1, or 1 over square root 2 1 minus 1. Also note that this is relevant for the understanding of Bell's theorem, which you will have to look at as your homework assignment. Note that you can calculate the expectation values in the states up, down, plus and minus of the operator sigma dot a that we discussed before. So if you calculate the expectation value in the state up, you will find that this is Z, whereas if you calculate the expectation value in the state down, you will find that this is minus AZ. And the same way, if you calculate the expectation values in the state plus, you will find AX, and in the state minus, you will find minus AX. Now, the important thing to realize before we can discuss the EPR argument is that we can create a state of two spin 1/2 particles out of a state that has spin 0, for example. And we get what is now called an entangled state. So specifically, if we say we start with a spin 0 state and we create two spin 1/2 particles by, for example, a particle decaying, then the state we get is the following. It's 1 divided by square root 2. And then we have the two possibilities. We have spin up for the first particle, tensor product with spin down for the second particle. And we have with equal probability the opposite case, where we have spin down for the first particle and spin up for the second particle. So this is the state we are interested in now. And notice that we can just rewrite this state and express it in terms of the states plus and minus that we had before. And if you do this, you find that it has almost, but not quite the same representation. It's 1 over square root 2. And then it is plus for the first and the second particle, minus the product minus times minus for both particles. So this represents exactly the same state, but in a different basis. And there's a third way to represent this that we also write down now, which is the situation where we represent the first particle in the basis up-down, and the second particle in the plus-minus basis. And in this basis, the two-particle state actually contains 4 terms. We have to write it as 1/2 up for the first particle, tensor plus for the second, minus up for the first and minus for the second, plus down tensor plus plus down tensor minus. So you see from this that the spins in z direction in this state are perfectly anti-correlated. So whenever we have spin up in for the one particle, we have spin down for the other, and vice versa. And the spins in x direction are perfectly correlated. So whenever we have spin plus here, we have also plus here, and whenever we have minus here, we also have minus here. So basically we can say that in a situation where we measure the z spin for both particles, if we find the first particle in up, we will find with 100% probability that the second particle will be in spin down. And if we measure the first particle in spin down, we will find with 100% probability that the second particle is in spin up. On the other hand, if we have a situation where we measure along the x-axis for both particles, we will find that if we measure plus for the first, we will with 100% probability find plus for the second. Whereas if we find minus for the first, we will, again with 100% probability, find minus for the second. But now in the third situation, where we measure the first particle with along the z-axis, and the second particle along the x-axis, if we find the first particle and spin up, then we have these two possibilities with equal probability. So we will find that if we measure the first particle up, we have 50% probability plus 50% probability minus, and the same if we measure spin down. So regardless of how we measure the first spin, we will always find that the measurement for the second particle will give us the two states plus and minus with 50% probability each. So of course this property is now known as quantum entanglement. And this notion of entanglement was actually coined by Erwin Schrödinger, who in response to the EPR paper, also in 1935, but later in 1935, wrote his famous paper, actually a series of 4 papers, where he also introduced his notion of the Schrödinger cat. And in this paper, he actually introduced the name entanglement that we now ascribe to states like that. So also important to notice that in the situation, once we have created a state where the two particles have these correlated or anti-correlated spins, we can bring the two particles arbitrarily far apart, and we can make the measurement of the one particle in a completely different position than the measurement of the other particle. And so this is the basis of the EPR argument. So before we come to the EPR argument, we need to talk about something that they introduce in their paper, and I switched to the paper for that, which is what they call the notion of elements of physical reality. So this follows the idea that of all the mathematical objects we use in the formulation of our theories, there need to be at least some objects that somehow correspond to something in nature. This is also sometimes referred to as the ontology of a physical theory. So there must be something in the mathematical description that actually gives us the connection to reality. So you can say, for example, in classical mechanics, those are particles that are actually there, so the theory is about the motion of particles. Or you could take, in quantum mechanics, you could take the point of view that, for example, the wave function in Schrödinger's equation is something that is, in some sense, actually there. In general relativity, we would say that space-time is something that is described by the theory that is actually something in nature. So there is a space-time, which is some physically real object, and the properties of that are described by a theory, which is general relativity in this case. And as a criterion to determine which objects have such reality, Einstein-Podolsky and Rosen come to this definition. They say, if, without in any way disturbing a system, we can predict with certainty, that means with probability equal to 1, the value of a physical quantity, then there exists an element of physical reality that corresponds to this physical quantity. So, what does that mean? You see in the text that they call this as a reasonable criterion. They write that this is a criterion which we regard as reasonable. And in fact, the criterion is actually much more than just reasonable. It is actually hard to deny in a consistent way if you want to claim that what you're doing is still a scientific theory. So basically what they're saying is, if there is some property which we can predict with certainty, so that means in any repetition of any type of experiment, this property always shows up exactly this way, then that's the very basic of the scientific method, that we would say, yeah, this is something which we now consider some truth about nature ourselves. Our goal as physicists is to understand nature, and we do this by experimental repetition. If in a repeated series of experiments we always find the same answers to something, then we gain trust in the description we have, and we say, okay, this is actually a property of nature. For example, energy conservation we observe in some experiment, and more experiments of different kinds show that there is actually some quantity that we call energy that is conserved. Then we start believing that this is a true fact about nature, that energy is actually there and is conserved in some sense. So this is what is behind the definition of Einstein-Podolsky and Rosen. And so if there is some property which we can predict with certainty, let me go back to the paper again. And the second part of it is if we can do so without disturbing a system in any way. That's in the first sentence. If without in any way disturbing a system. So this means whatever the physical state of our system, if we don't disturb it, that means we don't change anything about it. So whatever we find about it, whichever property this is, that always comes out as it is predicted with certainty. Whichever property this is must have been there all along, because we don't disturb the system. We do not change anything about the physical state, so just by logical conclusion, the state must have been this way already. This means that whatever we find, this property must be a property of our system independent of whether or not we do this experiment. Since the property will always come out this way, no matter which type of experiment we do, since our experiment we do does not change anything about the state of the system, it does not disturb it in any way, this must in fact be a property of the system itself. So, property of nature in some sense. And this is important. So this property must be there whether we measure it or not. So once we have accepted this definition of this criterion of reality, we can recall our system of the two entangled spin 1/2 particles and come back to the conclusions that we made about measurements. So we saw that if we perform a spin Z measurement, we can predict with certainty the state of the other particle. We know if we find spin up, a spin Z measurement will give us spin down for the other particle. So we can, in fact, by making this measurement, predict with certainty what the Z spin will be for the second particle. So according to this criterion, this must be an element of reality. So there must be some element of reality that represents the Z spin down of this particle, regardless of whether or not we measure it. And in the same way, the X spin, if we measure plus, we will be able to predict with certainty that the other particle will also have the spin plus. So also in this case, there must be an element of reality that belongs to the second particle that tells us this particle has the state plus. But now, of course, we have the contradiction that the quantum mechanical prediction tells us if we measure spin up, and we want to know, if we measure the z spin for the first particle, and we want to know the x spin, although the x spin must be plus or minus because it's an element of reality, the quantum mechanical formalism is not able to tell us whether we will find plus or minus. The quantum mechanical formalism just tells us, well, if you measure it, you will find either one of them with 50% probability each. So this led to the conclusion by Einstein-Podolsky-Rosen that something about the quantum mechanical formalism must be incomplete. The information whether the particle is actually in the x spin plus or in the x spin minus is missing in the theory. And now comes the last argument, or the last step, and this is how do Einstein-Podolsky and Rosen actually make sure that they do not disturb the measurement in any sense. Because you remember, that was the important criterion. We can predict with certainty the value of a physical quantity without in any way disturbing the system. So how do we make sure to disturb the system? Well, Einstein, having basically invented relativity and having invented the concept that nothing can be, no signal can be sent faster than the speed of light, had of course a relatively easy way to isolate systems from each other, which is simply by putting them far enough apart. If you can do the experiment here on particle 1 and you make sure that the two particles are far enough apart that no light signal could reach the other particle within the time that it takes you to perform the experiment, then you would certainly, if you believe in special relativity, you would certainly say there cannot be any way in which my measurement of the one particle could disturb the state of the other system, because this would be in violation of special relativity. And this is what we call a local theory, so a theory that has no non-local, faster than light influences on the other part of the system. So Einstein, Podolsky and Rosen, or Einstein in particular, of course, believed in this locality assumption so much that he saw this as a given and then concluded based on the argument that there must be something missing from quantum mechanics. Quantum mechanics is incomplete. And this did not change for 30 years until Bell came and formulated his theorem and his inequality. So in 1964, Bell wrote a paper on the Einstein-Podolsky-Rosen paradox. So it's already in the title that he's actually referring to the EPR argument and just wants to continue the argument. And what Bell actually did in his paper is that he formulated an inequality, which you can find here, that is about the correlation of different measurement setups in this EPR type experiment. What Bell's inequality shows is that assuming locality and assuming that there are some hidden variables, local hidden variables, which he calls lambda, so something that actually satisfies this wish of Einstein, Podolsky and Rosen to complete quantum mechanics, that if you have such a theory, you get these correlations that are in contradiction with the quantum mechanical prediction. So quantum mechanics actually predicts something different than what any what any local theory with hidden variables would represent. And the experiments that were done later showed that quantum mechanics is actually correct with the predictions. So the conclusion from Bell's inequality, together with the experimental results, is you cannot have a theory of hidden variables that is local and gives you the same predictions as quantum mechanics and the experiment show. So in conclusion, Einstein-Podolsky and Rosen have shown, well, the only way to keep locality in our theory is if we introduce hidden variables, if we add something to quantum mechanics. And what Bell shows is, no, this is actually not an option. Local hidden variables are not an option, are something that contradicts the experiment. So since local hidden variables are not an option, the only way to make sense of the EPR argument is you have to give up this assumption of locality. So what we learn from Einstein-Podolsky-Rosen together with Bell's argument, and what Bell actually proved, is that nature is in fact non-local. So there is a non-local influence if we measure the spin of the first particle. There is some non-local influence on the second particle. So you will hear a lot of statements on what Bell actually showed or what he disproved. Since a lot of those things are contradicting a bit the statement that I made, I should add some remarks here. So the first statement is correct, and it is that Bell disproved local hidden variable theories. But this often results in a misconception, which is the misconception where people miss the point that Bell's paper is based on the EPR argument. They just see Bell's paper by itself. So they often see it as if there is a choice. So since Bell disproves local hidden variable theories, well, you need to give up either the locality or the hidden variables. So then you're perfectly fine, then you can just keep locality and everything is nice as you want it if you believe in relativity, and the only thing you have to give up is the idea that there are some hidden variables in quantum mechanics. So you have to take quantum mechanics as it is, but then it is fine. But this is of course not a choice that we have, not because of what Bell proved, but because of the argument that Einstein, Podolsky and Rosen showed, that hidden variables are the only way actually to keep locality. So what EPR showed is hidden variables are the only way to keep locality, and then what Bell showed is, well, no, hidden variables are also not a way to keep locality, so you need to give up locality. The second thing that is even more popular and has become increasingly popular in the last 20 to 30 years, it hasn't been a thing that was much in the literature after Bell, but is to somehow account to this reality criterion that Einstein, Podolsky and Rosen give. And very often since the mid-1990s, people are not talking about locality anymore. They are saying the assumption in Bell's proof is local realism, whatever that means. So this is also some common misconception, because it gives you the idea that there are two components in Bell's proof, locality and realism. And again, if you have these two components, you basically have the choice to give up either of them, right? So you can either give up locality and have a non-local theory, but you can also opt to keep locality and give up realism, whatever that means. And sometimes it's even worse, and sometimes people refer to this EPR reality criterion as classical or something like that, which kind of seems to imply that it is something very natural to give up in a quantum theory. But as we have discussed, the reality argument is essentially the basis of doing science at all. It is what connects the mathematical formalism with the description of nature. So basically, if you give up on this reality argument, you're giving up on the idea of describing nature at all with your theory. Then all you have is basically some mathematical gymnastics that somehow has some correlation with outcomes of experiments. But you don't really say anything anymore about what are those things that I have in my theory, what property of nature do they describe. So this is not really an option unless you're willing to give up doing science altogether. And the third remark is about the notion of locality. So it's important to notice, because this is also often confused, that locality really means locality in the sense that Einstein-Podolsky-Rosen need it for their argument. So it means whatever I do with my first particle should not disturb the state of the second. And this is all that we need. There is no need for any sort of faster than light signaling or any particles be sent faster than light. So the fact that quantum mechanics, the standard quantum mechanics formalism, does not allow for superluminal signaling is not in any way a contradiction to saying it is a non-local theory in the sense of Einstein-Podolsky-Rosen. So this is also something that is often confused. And finally, the one assumption that Bell does make in his argument, and this is also the one way that you can get around his argument and keep locality if you really like it, the one assumption that he does make is statistical independence. If you read his paper, and you should read it as your homework assignment, I put it on the Moodle page, so please have a look at it and try to follow the steps that Bell presents, and try to particularly understand what are the assumptions that enter. It's not so much about the details of the proof. Try to really focus on what assumptions are made for the proof. And if you do that properly, you will notice that one of the assumptions, and the most crucial of the assumptions, is actually that the hidden variables that Bell calls lambda are uncorrelated with the detector settings. So you can also write this in the language of probability theory. You can say this means that, so Bell calls it rho, the probability distribution of the hidden variables, rho of lambda, and so this is a conditional probability, rho of lambda, and the condition that your detectors have the settings A and B, and this conditional probability Bell assumes to just be a rho of lambda. So the state of nature, if you want, doesn't care about how I choose the setting of the detectors. And theories that violate this assumption, for those, Bell's theorem doesn't need to hold, so those theorems can very well be local. And those theories are usually called superdeterministic. They are usually, so people don't like them very much because they seem quite weird. They seem a bit like allowing for conspiracies, and like, why should I not be able to freely choose the detector settings? Sometimes people also say that they are somehow in contradiction to free will, if you want. But you have to keep in mind that there are a lot of features of quantum physics that are very weird. So just the fact that something is weird shouldn't give us the right to dismiss it as a possibility. So if you take the theorem seriously and take the assumption seriously, then you have to recognize that there are essentially two options. Either the world is in fact non-local in the sense that EPR say, or statistical independence doesn't hold. So this is the lecture on EPR. In summary, so what EPR shows is that if we assume locality, then we can only account for the prediction of quantum mechanics if we introduce hidden variables. Then Bell proves that assuming statistical independence, there is no local theory of hidden variables that can reproduce the predictions of quantum mechanics. But since the experiment shows that the predictions of quantum mechanics are correct, we basically have only the two options. Either we accept that the world is non-local, or we accept that there is some sort of superdeterminism, so that there is no statistical independence. Yes, and any future theory that we would want to derive that from quantum mechanics, any future theory that we want that should merge gravity and quantum physics, any quantum gravity theory or any modification we want to discuss in this lecture has to respect this result. So that's why this EPR argument is so important. We don't really have to have any choice to go around that, whatever we came up with. If we want to somehow merge relativity with quantum mechanics, we need to somehow account for this non-locality that is very much against the principles of special relativity. And this is kind of, if you ask me, this is maybe the one crucial problem if you want to actually formulate a quantum theory of gravity. Has not so much to do with general relativity and has not so much to do with quantum field theory. It's at the very basis of quantum mechanics, where you have this non-locality, and this non-locality violates everything that we know about the principles of special relativity, not general relativity, special relativity. So in this sense, quantum mechanics is incompatible with special relativity more than quantum field theory is incompatible with general relativity. Okay, so this was the first lecture, and I'm looking forward to seeing you for the Zoom meeting on Wednesday and for the next lecture in 1 week.